Hello! Welcome to week 5 of Algebra 2 Accelerated Distance Learning Style. All right, so today, really exciting, we're starting a brand new unit, and this unit is sometimes called the trig unit or trigonometry unit. And so you're going to be learning about some of the things related to cosine, sine, and tangent, just like you did last year, but we're going to add to it. So you're going to have to remember some of the SOHCAHTOA things that you learned last year, but we're also going to take it and we're going to expand on it. So it's a really cool combination of things that you've learned in geometry and before, and also combining it with our new understanding that we're gaining about functions in Algebra 2. Now, I know we kind of took a little bit of a break from functions, the idea of input, output, for the last unit, which was probability, but this unit, definitely going to get back into it after a little bit of a break to look at some geometry, look at things more visually for a little while. So, yeah, let's take a look. There's a few different things we're going to look at. So let's go over the topic and the goal. We have finding coordinates. Now, I know that seems silly, like an X and a Y makes a point, but coordinates are related to triangles, to right triangles. So that's what we're going to be looking at for coordinates this lesson. Reference angles are a special type of angle that help us learn about something called the unit circle. Next week, we're going to be talking about the unit circle. So if you want to look up some extra videos to prepare yourself for next week, you could look up how to memorize the unit circle or how the unit circle works. But reference angles are something that are related to the unit circle. And then we're going to talk about radians and degrees. And radians are a different way to measure angles than degrees, which is what we're used to. And remember, whatever calculator you're using, we need to be really, really conscious of what mode we're in our calculator. So for example, if you're using calculator hashtag, which is the one that I've been using, you have to press the over button down by the infinity, and then make sure that you are in either degree where it says DEG or radian mode. We are not going to use GRA mode, which I believe is gradient mode. So it's either going to be degree, radian, and that's it. So we're going to start off with a question to hopefully get you into thinking about sine, cosine, and tangent. We're going to solve for the missing, or for x, which is the missing side, using SOHCAHTOA. And you'll remember sine is opposite over hypotenuse. That's what SO stands for. Cosine is adjacent over hypotenuse. That's what CA stands for. And then TOA is tangent is opposite over adjacent. All right, so take a look at these two questions and see what you can remember. I'm going to pause the video like normal, and then we'll come back together and work on it, and check our answers. If I can get this thing to pause. There we go. Okay, see you in a minute. All right, I am back. So let's take a look at what we figured out. So hopefully you were able to label your sides and figure out for this first one that you have the hypotenuse and you have the adjacent. Therefore, you do cosine of 52 is the opposite over the adjacent. To get x alone, you just multiply both sides by 18. And then I wanted to go over how to use a calculator to do this part because it can be a little confusing on some calculators. So you want to make sure that you're in degree mode because your angles are being given to you in degrees right now. So we have pretty simply 18 times cosine of 52. And that's 11.08. And we usually round to the nearest 100th. So 11.08 is our final answer. And we don't have units, so we're just saying 11.08 for our final answer. Let's take a look at this one over here. We can see that we have our opposite and we have our adjacent to 66 degrees. So we set it up with the tangent 66 is x over 12. And then to solve, you just multiply both sides by 12. And so putting it in your calculator, it should be 12 tangent 66. And then that is our answer. So we have 26.95 for our answer. So x equals 26.95 is our final answer. All right. So hopefully that's fresh in your brain now. Hold on just a second. Okay, we're back. Okay, so hopefully that's fresh in your brain, like I was saying. But if not, I'm going to put some extra resources up for you, an extra worksheet, and I'll link some other videos for you. So hopefully SOHCAHTOA will be refreshed in your brain. But the expectation is that you do remember how to do these trig ratios to solve for the sides of a triangle. But really, it's nothing more complicated than this that you'll need to know for solving triangles. Okay, let's get started. We have something called standard position. Standard position. So standard position is a way that we draw angles so that we can look at them in the same way and compare them. And the way that we're going to look at standard position angles is it's an angle with its initial side, which means its starting side, on the positive x-axis. So looking down at this picture we have here, this is the positive x-axis right here, right? If we have, here is our origin 0, 0. We have this circle around the origin, and the positive x-axis would be where I put that green arrow there. And then its terminal side, which means its ending side, is placed according to the counterclockwise direction of the angle. So basically the idea is once we know what angle we're looking for, we're gonna go in the counterclockwise direction until we get to it. So let's do some examples together, huh? The first thing you're going to do when asked to draw something in standard form is you are going to draw a picture of it. So teacher example A, I'm going to say, first of all, I'm going to draw my axes, right? And then I'm going to always start from the positive x-axis. So I'm always going to start by drawing my initial side right there, no matter what the angle is. Then I look at my degrees. I have 150 degrees. So hopefully you're thinking in your head, okay, well, this would be 90 and this would be 180. And so it would be somewhere in between there. That's great logic. I have also taken into consideration that we're distance learning. So I'm providing the scaffold for you that has all the angles that you will see us do on it. So if you are not sure exactly where to put the angle, and don't worry, it doesn't need to be perfect. You can say, okay, 150, 150, where's 150? Oh, there's 150, okay. So the angle that we wanna draw looks like that. So we come back over to our self-drawn axes and we say, okay, 50, right about there. And then it's polite to label the angle like that. Sometimes I might forget, but hopefully you guys will get in a good habit of labeling the angle in the counterclockwise part of it. All right, let's move that aside and let's do another example. Let's do part B, question B. Okay, first step is still the same. No matter what, you draw your axes, you draw your starting side of the angle, and then we're looking at negative 240 degrees. All right, so let's look at this. We're gonna erase what I drew, starting here. Negative 240, well, 240 is right here, right? But that would be if we were going in the positive direction. Whenever you are given a negative direction, you have to go clockwise to get to your terminal side. So one way to look at it is to look at the shape, right? So you know you're going all the way here, right? And so if you're going the same amount but in the opposite direction, you would say, okay, I'm going in the negative direction, and so I would stop there. Some of us are really good at being able to just see that in our head and make that with the symmetry of the angles, you're able to do that. Some of us not so much, and that's okay. A way that you can find where that angle is without having to just see the symmetry of the circle is you could do 360 minus 240. I'm sorry, it was, 240. And that'll give you 120. And so then I can see, okay, well, if I went in the positive direction, it would end at 120. So I know that my angle would be there. So the moral of the story, let's finish this guy off. Negative 240 means that if it was positive, it would be down in the third quadrant. But since it's positive, it's going to be up in the second quadrant. And so we go like this, and then we would label it with negative 240 degrees. All right, so this is your introduction to standard form. It's your turn to try a couple questions without me. So just like normal, go ahead and pause the video and try them on your own. And then when you come back, I will check your answers with you. Okay, hello, back at it. So we are gonna just check our answers. Hopefully that wasn't too tricky for you. The first one is 210. That one is just on the circle that I gave you over here. So hopefully you're able to just know that you need to write your initial side and your terminal side and then label it in the correct direction. And then our other example, you can kind of see it. Maybe it's a little confusing because it's with the background stuff, but negative 45 degrees. Again, if I got confused about where that should be, I could do 360 minus 45, and then that would give me 315. And I can see over here, my 315 is right here. And so you can see that. Also, 45 degrees is halfway between 0 and 90, so you know it's always going to be the one that's in the middle of the quadrant. So something to keep in mind. All right, so hopefully you understand how we're going to be looking at angles for the next unit, the next few weeks here. And let's bring in a new idea. And you might have been wondering, what are all these weird things hanging out on the outside of our degrees? Those are called radians, and it's just a different way to measure angles in a circle. They're the same as degrees, except for instead of just cutting a circle into 360 little tiny parts, we say that we are going to measure the angle based on its ratio of the circumference to the radius. Now, you don't need to know that, so don't worry too much. It's just important that you understand that the reason why we have these pies in there, and especially why we have this idea that we're starting at 0 and then we go all the way around and we end at 2 pi. So 2 pi is the same as, this would be 360 degrees all the way around, is that when our radius is 1, right? If we're looking at the circumference formula, if our radius is 1, then 2 pi times 1 is 2 pi. So that's why a whole circle, if the radius is 1, is 2 pi. So don't worry about that too much. Just know that 2 pi is a whole circle, starting at 0 to 2 pi, 0 to 360, same idea. So here is a conversion factor. Now, most of you, I hope, in science have dealt with conversion factors where you have to convert from inches to meters or from kilometers to feet or something like that. It works the exact same. So a conversion factor is just a fraction that you multiply by your number in order to convert it. So since 360 degrees is the same as 2 pi, if I wanted to move from degrees from radians into degrees, right? Radians to degrees, then I would multiply it by 360 over 2 pi, or to simplify that, 180 over pi, right? So we're going to be using 180 over pi when we want to convert from radians into degrees. Now, if I wanted to go degrees into radians, right, the opposite of what we were talking about up here, then all I have to do is just switch the fraction around. And so 2 pi over 360, same idea, and then it's pi over 180. Again, same fraction, just reduced, so it makes your life a little bit easier. So let's give it a shot. I have a lot of examples here. I don't think that you're necessarily going to need all these examples. I know my lessons, my recordings are really long, and that's just because I don't have a bell schedule to go by, right? I've said this in most of my videos, but if I had the chance, I would do way more examples than I do in a normal class period, because I really think that, doing examples is helpful. However, we just don't have enough time. So I'm going to really soak up this extra time that I have. If you don't need this extra examples, you can skip through this and just try the student examples and check your answers and get on with your life, okay? Okay, so let's take a look here. We have question A is 45 degrees. So what we're going to do is since we have degrees, we know we need to go into radians. So I'm going to write down my number, 45 degrees. And then the way that I think about this is I want to get rid of degrees, so I put them on the bottom. I'm trying to divide out degrees, so I put the degrees on the bottom. Whatever I want to get rid of, I put on the bottom. Okay, and then it's pi on top. Now, I could just put everything into my calculator, and then if you have one of these fancy calculators or another calculator that'll give you exact answers, then you can just do this whole thing in one step on your calculator and be done. However, not very many of us have these calculators right now, so we're going to go through and do it using a reducing fractions method. So 45 degrees, I know that 45 is the same as, 180 is the same as 4 times 45 degrees. And so the 45 that's being multiplied and divided simplify to 1. And then what is left is pi over 4. Now you'll notice here that this exact amount is on the circle that we just looked at, right? This is pi over 4, 45 degrees, so we know our answer is correct. Now, if you're a little rusty at reducing fractions, a trick you can use on your calculator is to go to the second screen and use your fraction and ignore the pi on there. Just pretend it doesn't exist. And you do the 45 and then you do over 180. And then it gives you 0.25. But something that you can do is press the number to fraction button that's down there by the EE button, and it'll change it into a fraction. Now, you know it's 1/4, but you also know you have a pi on top, so pi times 1 is pi over 4. So that's one little cheat that you can use to reduce a fraction if you're feeling a little rusty. But I hope you take this opportunity to work on your skills. All right, let's look at B. B is pi over 2. Now, again, same logic. If I want to get rid of the pi, right? I want to get rid of radians. Then I'm going to put the pi on the bottom of the fraction because I want to divide it out. I want to simplify it to 1. And now this one's a little easier because I know 180 divided by 2 is 90, right? So I could just make that step, but let's just do the step so that we have it done. Pi over 2 times 2 times 90 degrees over pi. And then we know the pi's would simplify to 1 and the 2's would simplify to 1. And so our final answer is 90 degrees. Okay, let's take a look at our unit circle. the circle where I have all the degrees and radians written out, up here, and I see that pi over 2 is 90 degrees. Now, our last one was 45 degrees, which is pi over 4. Makes sense, right? A half is twice of a fourth. 90 is twice of 45. So although we got those silly pies to look at with it, the fractions still make sense in relation to each other. Okay, let's do C. Oop, almost dropped my pen. C is negative 30 degrees. And okay, I'm gonna start skipping steps a little bit here. So pi over 180 degrees. I know that 30 goes into 86 times, right? 8 divided by 3 is 6. So this would be, don't forget the negative pi over 6 when we reduced it. And then we could take a look here at our picture. Now it's negative, right? But we know that 30 degrees is pi over 6. So if we went the other direction, yeah, it's not going to be listed as such, but we do know that 30 is pi over 6, so negative 30 is negative pi over 6. All right, 2 more for me, and then you get to practice these, A, B, C, D. Oh, 3 more for me, I guess. All right, we have pi over 6, and now I'm starting to see some patterns, right? Pi over 6, and then, wait, if negative pi over 6 was 30 degrees, okay, so that means pi over 6 is 30 degrees. All right, and then we just saw that on the wheel as well. So I'm hoping that repeating these specific angles that are going to be really useful for next week. We're starting to see some patterns, right? So it's good if you're starting to say like, hey, I shouldn't have to redo that question again because I just did one that's the same answer. That's great. If you're starting to notice that, keep it up. All right, so 300 degrees, pi over 6, we know that 380 are both divisible by 60, and so we can say this is the same as 5 pi over 3. Let's do that one a little slower, and we can also just, let's do that one a little slower just so we can see the steps, because that one's a little more complicated. So I know that 300 is 6 times 50 degrees, and I know that, 60 times 5 degrees. Sorry, one more time. 5 times 60 degrees there. And then this is 3 times 60 degrees. And so the 60s simplify to 1 when they're multiplied. Now this 5 gets multiplied by the top, right? Whenever you have a whole number in front of a fraction, you multiply it by the top. So it's 5 pi. And then this 3 is still hanging out on the bottom there. Let's take a look and make sure that we got that correct on the unit circle that's above. The unit circle says 5 pi over 3 is the same as 300. Yep, that's that spot on the unit circle, which makes sense, right? We had to go all the way around to get to 300, and then there's 60 more to get here. Okay, 2 more from me. Again, or 1 more from me. Again, feel free. You don't need to watch every single example. If you feel like you're getting it, go ahead, skip ahead. F is negative 3 pi over 4. I'm going to try and get rid of the pi, which means I need to put the pi on the bottom. All right, and so I'm trying to think. I know 45 times 4 is 80, 180, so I'm going to do negative 3 pi over 4, that's going to stay the same, times 4 times 45 degrees over pi. And then I know the pi's simplify to 1, and the 4s are going to simplify to 1, and then 3 times 45, that's 135. If you don't know that, that's okay. You can always do 3 times 45 and get 135. So this is equal to negative 135 degrees. Now, negatives aren't on the unit circle, but if you wanted to check your answer, you could always look at positive 135. and see that positive 135 is at 3 pi over 4. So therefore, negative 135 is at negative 3 pi over 4. Okay, I got some examples here for you. I got your reference unit circle to help you do this. Go ahead and get started. Pause the video, and then I will check back with you when you are done. Check your answers with me when you're done. All right, so here's your answers. Hopefully this isn't anything too challenging for you. I mean, the answers are all more or less on the unit circle that I've provided for you, but I also hope that you are taking some time to really trying to learn how to use the conversion factor as well, because both methods are very, very helpful. Sometimes if you're going on to pre-calc, you're going to be given degrees that are not on the unit circle. I decided, because we're doing distance learning, I was going to keep it only to those these ones that are listed here. But in pre-calc, you might be asked to know 15 degrees, right? And then you'll have to use it's not on the circle for you to memorize. And maybe I'll give you 70 degrees in pre-calc, or your pre-calc teacher will. And so anyway, I just wanted to put that out there that, yeah, I'm keeping it pretty simple for this, but I want to make sure that you know that it is going to get more and more challenging. So I hope you are challenging yourself to use the conversion factor. One interesting answer that I found was that this one with the 180 and this one with the negative pi, it's the same angle, right? If you just look at it, they're both like a flat line, right? If you do a 180, you turn around, you're going the opposite direction. But on this one, we had to draw the direction going this way. And then on the other one, we had to draw the direction going this way, because one is positive and one is negative, even though they both end up with the terminal side in the same spot. Okay, so let's talk about something that's really, really, really useful next week. This week, it's just going to be kind of more memorizing the vocab and hopefully discovering something that is interesting, an interesting occurrence in trig that you might have noticed when you were in geometry, but didn't have a good explanation as to why it happened. So reference angles, it's the angle that's formed by an angle in standard position. So we just learned how to do standard position. Sorry, I'm getting some emails in here, in standard position. And then it's you go down to the nearest x-axis. Now remember that the x-axis is this black, this pink axis that I am highlighting in pink here. And that's really important that you remember that. Reference angles have nothing to do with the y-axis. So just ignore the y-axis completely. Reference angles only have to do with the x-axis. Okay. So the reason why it says, and you can ask yourself what angle would my triangle be if I was making it in quarter one? So maybe that would be a helpful thing to think, and maybe you can understand that in just a minute. Why did I put the word bow ties here? So the reason why I put the word bow ties there is because we can make 4 of the same triangles for every single pattern in this unit circle. So take a look at these red lines that are in our unit circle. They kind of, if you were to draw this way and draw this way, they kind of make a bow tie, right? That you'd wear around your neck, or just a bow. And that pattern is really, really cool, because if we're looking at it in terms of the x-axis, every single one of these triangles, right, this one, this one, this one, and this one, they are exactly the same triangles. Okay, let's take a look at the next pattern. The next pattern happens with the blue lines here. So the blue lines, if we're going to go across, and we're going to go across, and we're going to go down, and we're going to go down, and we're looking at them in terms of the x-axis. They all make the same triangle with the x-axis. It's just flipped around, right? It's the same angles, just flipped around. So that's something that we definitely want to keep in mind. And then finally, let's look at our final one, the green bow, the tallest of the bows. We got high and high. All right, and then they're coming straight down, making a little bow tie if the black was like the neck of your suit that you were wearing. And then we can see, again, this triangle is the same as this triangle, is the same as this triangle, is the same as this triangle. And they all make right triangles with the x-axis. All of these triangles are making right triangles with the x-axis. And this is also in red, but that's okay. Okay, so why do we care? Well, there's a lot of patterns that are going on here. And again, we'll talk more about this next week when we start to memorize the unit circle. But I want you to notice something really interesting is that notice all of these have a denominator of 3 for that reference angle. And then looking over here, all of these have a denominator of 4 for those reference angles. And all of these have a denominator of 6 for these reference angles. And that's not a coincidence. That's why radians are so interesting, because they have these really interesting patterns that help us learn and memorize unit circle. Okay, so let's do some examples. We are going to draw out some angles that are in standard position, and then we're going to find the reference angle. The only thing I threw in here, just to mix things up a little bit, is I say we are going to make sure that the distance, oh, oops, just kidding. So ignore this distance thing. That should be ignored. I apologize for that. So ignore all those distances. Okay, so first thing we're going to do is draw it in standard position, and then we are going to find the reference angle. So for A, we have a standard position, which would be right there, 45 degrees. Hopefully you guys are good with that by now. And then our reference angle is the angle that this makes if we drop down to the x-axis and we make a right angle. We want to know, what is this angle right here? Well, it's 45 degrees because we just went up 45 degrees, we come down 45 degrees. So the way that I write this as my answer is reference angles equal 45 degrees. Okay, so let's try B. You'll notice B is in radians, so we might need a little bit more thought in this next one, but hopefully it's not too tricky. Actually, it is kind of a weird one, so we'll take a look. Hopefully they'll be more normal after that. So I want to know, I went up to pi over 2, right? And we could use our circle reference to help us if we needed to. This is pi over 2. I could either go down to the x-axis over here or the x-axis over here. Either way, I'm going to be going the same distance. So my same number is my reference angle. So I guess it was good that you saw early on that the reference angle can be the same as the original angle, but also maybe a little confusing to start off with those examples. So let's see, let's try question C, and hopefully it's a little more clear. So this one, again, is going to be pretty clear that here is my standard position, and then my angle is negative 30. So I'm going to go negative 30 degrees. And I'm going to form a triangle with the x-axis. Now, I don't want to go that way. That is the y-axis, right? I want to go to the closest x-axis. And then I want to know, what is this angle that I just formed right there? Well, even though we went down to get to negative 30, we would always write our reference angles as positive. So it's 30 degrees to get to the x-axis is the way to think about it. Don't worry about which direction you're going. You always consider it to be positive. All right, let's look at question D here. We have 2 pi over 3. This one's a really good one. So we got, okay, so here's our standard position, 2 pi over 3. If you needed to look at the reference circle, that's okay. I've been doing this for a while, so I didn't have to. 2 pi over 3 is that distance there. Now, the closest x-axis, right, would not be going all the way back. It would be going straight down, forming a right angle, and then I want to know, what is that angle I just formed with the x-axis? Okay, couple different ways to approach this. We can look back at our reference angle bow ties that we made, and we can see that 2 pi over 3 is right here. It has the same reference angle as this, and as this, and as this angle here. And that is the key one, right? If our angle is pi over 3, then our reference angle is also pi over 3. Another way to think about it is you are 2 pi over 3. There's one more pi over 3 left to get to 180, right? There's another 30 degrees, or sorry, there's another 60 degrees between 120 and 180, and we know that 60 degrees is the same as pi over 3. So the question you're asking yourself, again, is what angle would my triangle be making if it was in quadrant 1? So what in this part of the unit circle? So the reference angle here is pi over 3. Okay, still got 2 more for me. Again, if you feel like you're understanding this, you don't need these extra examples, feel free to move ahead. You can go and try the student examples and then just check back that you got your answers correct. Let's do E together. All right, E is in degrees. That rhymes. And it's 300 degrees, so almost all the way around the circle. And my question is, what is the amount that it takes me to get back to the closest x-axis? And so, again, a couple different ways to look at this. I could look at my bow tie reference. Here's my 300, right? So if I look into the quarter 1, I see it's 60 degrees. That's my reference angle. Another ways to think about this is you're getting to 300 right here. You know that it's 360 degrees to get all the way around. So 360 minus 300 means there's 60 degrees left to get back to the x-axis. So the reference angle is equal to 60 degrees. All right, last one for me, and then y'all get to try your own. All right, this one's kind of a tricky one, but it's a good example. We have our initial side always on the positive x-axis, and then we're going negative 5 pi over 4. So on my reference, I know that 5 pi over 4 is right here, right? That's my 5 pi over 4. But if I'm going the opposite direction, then I can say, okay, it's not going to be 5 pi over 4 positive way. It's going to be 5 pi over 4 the negative way. So we're going to go 5 pi over 4 is going to be right there. So this is negative 5 pi over 4. Now, the closest x-axis that we can create a right triangle with is that negative x-axis. So you can think to yourself, how much is missing in between the place where my terminal side is and the x-axis? Well, I know that it's 5 pi over 4, right? So this is 4 pi over 4 to get here, and we'll go into this more. This is just one strategy. And so then this must be 5 pi over 4 here, so I know it's pi over 4. If that confused you, don't worry about it. Let's just use our reference, right? So if we're at the over 4s, right? All of these are over 4, over 4, over 4, over 4. I know that I am here, but what would the angle be if I was in quadrant 1? It would be pi over 4. All right, so we know that our angle is pi over 4 for our reference angle equals pi over 4. Whew, okay, that was a lot from me all at once. So feel free to take a break, get up and stretch, and then you're gonna try your student examples. Again, I'm gonna pause the video for a little while. You're gonna practice those examples, and then when you come back, we'll check our answers together. Okay, I am back. Got a little cold in my house. I got my jean jacket on now. Okay, let's take a look. You might have noticed in the other video that the examples were different, but your version should be correct. So I just switched around the examples, made a couple little in the moment fixes. So hopefully we're good to go here. I didn't think any of these were too tricky, but one thing that I did want to, a couple of them I did want to reference. So one that I want to reference specifically is this one right here, because I think it teaches us a good lesson about subtraction to figure out reference angles rather than using the guide that I gave you. And the idea is that we're going negative 210, right? So this is all the way negative 210. But we know that negative 180 would be here, right? And so we're thinking, well, we're going, how much past 180 did I go? I went 30 past 180. So that means I have 30 degrees to go to get back down to the x-axis. So you could say, a couple different ways to do it, but you could say like 210 minus 180 and then get 30 as your reference angle. Remember, reference angles are always positive no matter what direction you go in. You always consider them positive because you're asking yourself the question, what angle would my triangle be if it was in the first quadrant? Okay, so let's keep going. Oh, that's not correct. This should be just pi over 4. Just pi over 4 for that one. My bad. Okay. Let's go on, and these next examples, they're not really tied to a definition necessarily, other than we're going to use the idea of a coordinate plane, and we're going to find the coordinates of points given a angle and a line segment length. So let's just get into these examples. These examples are going to help you get really prepared for next week's unit circle and having to understand where the unit circle comes from and how to memorize the unit circle. Okay, so let's start with A. The question says a line segment starts at the origin 0, 0. Okay, that's simple enough. And extends a distance D at an angle theta. So that little angle symbol, you probably saw it in geometry. Remember that you say that theta. Okay, so here is our 0, our starting point, right? Always in standard position. And then our angle goes to 45 degrees. So we're going out 45 degrees in a distance of 2 units. So we're going out 2 units at an angle of 45 degrees, and this is a length of 2. And what I want to know from you is what is the coordinate of that point? And we're going to use that same idea that we did from our previous examples, that we have a height that comes straight down, and we have a length that goes straight out, and they make a right triangle. This length is the x part of our coordinate. This length is the y part of our coordinate. And so we are going to be finding the x and y for our triangle. That is our coordinates. That's why reference angles are so amazing, is because they help us find the coordinate of the point that is at the end of that line segment, depending on how long the line segment is. Okay, also, super exciting. We get to go back and use our geometry skills that we had from last year. So it's going to be pretty simple though. It's just going to be sine and cosine. That's all we have to think about. So we know, let's try to solve for the x first, okay? So I'm going to use blue for x. X is right here. We know we have an angle. We have the hypotenuse and the adjacent. So that means we have that the cosine of the angle is equal to the adjacent, which we don't know, it's the x-coordinate, over the hypotenuse of 2. Now, you're not going to really have to do this over and over again. You'll start to see a pattern, and you can just kind of skip over the actual solving part, but multiply by 2 on both sides to get x alone. And we see that 2 times cosine of 45 is equal to 1.14, and that's equal to x. And so that would be our x coordinate here. And we will rewrite that at the end. I'm going to use red for the y. So the y is right here. We know that we have our angle, we have our hypotenuse, and we want to know the opposite. So that means we're going to set it up. Sine of 45 is equal to y over 2. And multiply by 2 on both sides to get the y alone. We get 2 times sine of 45 is equal to, and you get the same thing. You get 1.41 is equal to y. And the reason why you always get the same thing when you have a reference angle of 45 degrees is because isosceles triangles, right? They have the same angles and they also have the same side. So if you could start to pick up on that pattern, it might save you a little bit of math. Okay, so what is our final answer? Our final answer is the x coordinate is 1.41. The y coordinate is 1.41. So on your formative and summative assessments, oops, I put the decimal in the wrong spot. On your formative and summative assessments, you are going to be typing in those coordinates, and that's going to be how you show you understand how to find the coordinates. Again, if this is making sense to you and you want to try it on your own, feel free, skip ahead. You don't have to watch me do all of these examples. I'm going to do 6 examples. It's a lot. I understand if you don't have the patience for it. Feel free to try it on your own. Come back if you need it. This is just me giving you that extra help. Hopefully, because, if you need it, you need it. If you don't, then skip it. Okay, let's keep going. We are going to do question B now. So question B is kind of interesting because it has the pi over 2. So question B, and let's take a look here. We have the angle. I'm going to draw it out. Here we go. There's my initial side, and then my terminal side is going to be at pi over 2, which is straight up and down. Again, feel free to use the reference if you want to, but hopefully these are you're starting to remember where things go. And then my distance here is 1, so that's my hypotenuse. Now this is a strange thing, right? Because we're dropping straight back down. And there's no triangle there, right? If it's a straight up and down side, how are you supposed to drop down and make a right triangle? Well, let's see what happens if we just set it up exactly the same as we did before. What happens if we say, okay, the cosine, let's do the cosine first. Let's do it in blue. Cosine of the angle we're given, we're just following the pattern of pi over 2, is equal to x over 1, which we could just say that's equal to x, right? You don't have to divide by 1. And so what happens on our calculator, we want to make sure we're in radian mode, and we're going to all clear. So that AC button is kind of useful on this thing. And we're going to do sine of, to go back, pi over 2. So I could use the divide here, or I could use the fraction button if I wanted it to be a little more clear. And I get 1. Oh, I said sine, my bad. So I want to do cosine. Okay, 0, right? So they're saying that our 0 is equal to x. Let's keep going. Let's try the sine now. Well, you just saw it. So the sine of pi over 2 is equal to the y value, and then so 1 is equal to the y value. Okay, so what does that mean that this point has a point at 0, 1? That makes total sense, right? Because it's on the y-axis and it has a distance of 1 from where it starts to where it ends. So hopefully you think that that's pretty cool. Even though it doesn't make a triangle, the trig functions still work. Okay, let's do another example here. Again, skip ahead if you would like. We have question C. Okay, C, we're going to draw our picture. We have negative 30 degrees, our first negative. Here's our initial side, and our terminal side is at negative 30, which goes down like this. And so we are going to make a triangle back up there. And what we want to do is we want to find what are the coordinates of this end point there. Okay, so a few different ways we can do this. Again, let's take a look at what's really going on. We know that our x is going to be here, and we know that our y is going to be here, and we know that our reference angle here is going to be 30 degrees because it was negative 30 to get down there. It's going to be 30 to get back up. So now we can do our math, and I want to show you something really cool. Cosine of 30 is equal to, what was our distance? Our distance was 0.5. Okay, so 0.5. So we have x over 0.5, and then to solve, I would just multiply by 0.5 times 0.5. In the future, I'm just going to kind of skip that part and just write it as 0.5 times cosine of whatever, or 3 times cosine of whatever. But we have 0.5 times cosine of 30 is equal to our x value. Okay, let's see. We are using degrees. Make sure you're in degrees. We're going to go to cosine. Oops, okay. Cosine of 30. And I got 0.87. We're going to round to the 100th. 0.87 is equal to x. Okay, but watch what is really cool. This is so cool. You know how I went to all that trouble? I guess it wasn't that big of a deal, but I changed it from a negative 30 degrees to a positive 30 degrees because I wanted to use the reference angle. Well, if you don't want to do that, you can just keep it at the given amount, and it'll be what? It'll give you what? The same answer. Very, very cool. Let's see what happens with the y value now. Okay, so we have y. Oops, that's not what I want to do. I want to do the sine. Oh, so sine of 30, and I'm going to use positive 30, is equal to x over 0.5. Multiply by 0.5 on both sides. And then I get, so the answer is 0.5 times sine of 30. And I get 0.25 or 1/4, whichever you want to use is fine for now. 0.25 is equal to x. Now, that's true. The length of that side of the triangle is 0.25. But notice the y value is below the x-intercept. So therefore, it's going to be a negative coordinate. It has to be negative 0.25 to be there. And the x value is positive because it's in the positive x direction, so 0.87. So instead of having to think harder by using the reference angle, what you could do is just not use the reference angle, put in whatever answer it wants you to, or whatever angle it wants you to use, if it's negative, positive, doesn't matter, and it'll give you the actual value, the coordinate, and you don't have to think about whether it's positive or negative, it'll just tell you, and then you can double check. Ah, so cool. Okay, let's try another one using the actual angle instead of the reference angle. All right, question D. Again, if you're feeling like you're starting to get it and you want to skip ahead, feel free. We have this initial side. Our angle is 2 pi over 3, so that's right here. And then our length is 2. Okay, so now the reference angle, if I wanted to make a triangle, I would come down here and I would make a right triangle, and I'd know that I could look up my circle and figure out that the reference angle here for 2 pi over 3 would be pi over 3, right? Pi over 3. And then I could use pi over 3, but I want to show you that you can just use 2 pi over 3 and it'll give you the proper negative x because we are trying to get this point right here. Okay, so let's do it. Cosine in blue, cosine in blue, always doing the x first because the x comes first here. So we got cosine of 2 pi over 3 is equal to x, but we got to multiply by 2 because it's a length of 2. All right, so let's change this up. 2 times cosine of 2 pi divided by 3. And then I think I need to change it back to, yep, rad. Okay, let's do it. I'm so excited. Yeah, I got a -1. Very cool. So this would be -1 is equal to x. And that makes sense, right? Because we're on this side of the y-axis, so we have a -1 for our x. And then our sine is going to be the same thing. 2 times sine of 2 pi over 3 is equal to our y value. That's our height. So 2 times sine 2 pi divided by 3 is equal to 1.73 for our y, which makes sense. It should be a positive y value because we're above the x-axis. So 1.73 goes right there. All right, one more from me, 2 more from me, actually, and then you get to go ahead and try some of these on your own. All right, so there's our example D. Let's do example E. We got our picture for 300 degrees. So 300 degrees is right here. And we know that if we wanted to make a picture of what's going on, we're going to make a triangle that helps us see that this is our end point. We want to know what are the coordinates of that point. The cosine is going to help us find the x, and the sine is going to help us find the y. And we know, let's see, for E, we had a distance of 0.5. So everything's going to be multiplied by 0.5. Let's do it. Always do cosine first because it comes first. We have cosine of, we didn't look at the angle yet. So this is 60, right? Because it's the rest of the way back to 360. So we could use 60, but then we'd have to think about whether it was positive or negative, the x and the y, and think about where we are in the coordinate plane. So I'm going to try and just use our value of 300, and then it'll give us our proper negative and positive values. I bet you guys were wondering the entire time in geometry why sometimes you might get a negative length, and you were like, that doesn't seem right. I'm not supposed to get a negative length. And that's why, is because you're in different parts of the unit circle. So yeah, kind of cool. I think it's interesting. Okay, let's do 300. Let's do 0.5 cosine 300. Let's make sure we're in degrees. We want to be in degrees. All right, 0.25. So that's going to be here, 0.25. And then finally, our sine. So if you just go back and you change this little part to be a sine, it's a little time saver I figured out. This is going to be negative 0.3433, negative 0.43 is our 100th place rounding. And we're done. I guess I didn't really write it out, but hopefully you were able to see how that works. And hopefully you're starting to like be able to be like, oh, okay, I can skip steps. I don't have to write everything out. I know that X is cosine, Y is sine. I multiply by the length. Starts to get a little bit more of a pattern for you. All right, let's do our last one here from the teacher examples. We have negative 5 pi over 4. That takes us right up here, negative 5 pi over 4. Again, our reference angle brings us back down here. We know that our coordinate points here and here, we could find them using the reference angle for the X and for the Y. But then we'd have to think about whether they were positive or negative. So let's use our negative 5 pi over 4, and then our calculator will do the negative and positive thinking for us. Okay, so I'm going to kind of skip some steps on this one. I'm going to say that my length was 3 for this question. So my X is always cosine, so it's 3 cosine. And then this was negative 5 pi divided by 4. I need to make sure I am in radians. There is my X value of my coordinate point. So negative 2.12. And then here we go, doing the sign in red. So same exact thing that I'm putting in my calculator, but I'm changing it from cosine to sine. And so that's 2.12. And then if we just want to double check that makes sense, it should be negative X because it's to the left of the Y-axis, positive Y because it's above the X-axis, and they should be equal, right? Because we have a pi over 4, we have a denominator of 4, and so therefore we're going to get a reference angle of 45 degrees, which means we have an isosceles triangle, which means the X and the Y are going to be the same. Okay, that was a lot of examples from me, so hopefully you guys are feeling confident. I'm going to pause the video and then we'll check your answers together in just a minute. If I can figure out how to press pause. Okay, there we go. All right, hopefully you guys had some success, and I just put the answers down for you guys to check your answers. Hopefully I don't have any mistakes. But if I do, everyone makes mistakes, nothing wrong with that. I always do my best to try and make up for my mistakes, and you guys do too, so that's awesome. You do have a challenge question on your notes. It's not showing up on the screen here right now, and that's okay. If you want to try the challenge, it will be on the teacher notes. So go ahead and go on to the teacher notes if you want to check your answer to the challenge or generalized question there. As always, keep up the great communication. You guys are doing awesome. I have just given some people some pointers on communication skills in the last week, just as we get more and more into this. Just trying to help you out. Try to send a screenshot, again, of any questions that you have. Screenshots really help me out knowing what questions you have and how to answer your question. Or, if you want to send me even better, a picture of or a screenshot of what you've tried to do, and that way I can try to find your mistake. That helps me out a lot too, because then I'm seeing that you're putting in effort and I'm helping you with your own effort. All right, Good luck this week. New stuff. Put in that effort. Do the worksheet. Try really hard on the formative. And good luck on the summative.